So let's take a look at example 6 here. This is a trig function that we're being asked to graph. So again, as we've done with the other problems, I know that finding the domain comes later in the problem, but let's do that first, just so that when we take the first and second derivative, we don't accidentally include something that's not part of our domain. So first of all, let's note that because this is a trig function, that it is periodic, and that the period of cosine and sine are both 2 pi, right? So period is 2 pi. So we are going to just look at a very specific period of 2 pi, and that is, we're going to look at the period that goes from negative pi over 2 to 3 pi over 2. Right. The distance between negative pi over 2 and 3 pi over 2 is 2 pi. The reason that we're choosing this one over, let's say, 0 to 2 pi or 2 pi to 4 pi, something like that, is because of the denominator here. So we can pick any period, any 2 pi period that we want, but if we pick negative pi over 2 as our one end point, note that when we do sine of negative pi over 2, so that's down here on our unit circle, and its coordinates are 0, negative 1. So when we plug in negative pi over 2 here, we're going to get negative 1, and 1 plus negative 1 is 0, and so the function is undefined at that point. Likewise, if instead of going this direction and getting to negative pi over 2, we go this direction and get to positive 3 pi over 2, same thing. That when we plug in 3 pi over 2, we get negative 1. 1 plus negative 1 is 0. It's also undefined at that endpoint. And so the reason that we're picking this interval in particular from negative pi over 2 to 3 pi over 2, not including the endpoints, is because at the endpoints we have our asymptotes, our vertical asymptotes. We are not interrupted by any vertical asymptotes in between here. So this is a really good interval to pick, just so that we're not having to deal with asymptotes in the middle of it. Again, you certainly could choose 0 to 2 pi, but then you're going to have to deal with asymptotes in there. Okay, and so what that tells us in terms of the domain is that when we're just restricted to this domain, it's defined on negative pi over 2 to 3 pi over 2 open interval. And let's just note that there are vertical asymptotes at x equals negative pi over 2 and x equals 3 pi over 2. And again, we'll get to that page in just a second. We'll rewrite it there, but for right now, let's just comment that that is what the vertical asymptotes are, and we're just restricting ourselves to this domain. Okay, so then let's talk about the first derivative. All right, so we're going to use the quotient rule right here. So f prime of x is going to be bottom times the derivative of the top. Remember, derivative of cosine is negative sine. And then minus, shoot, I shouldn't have done this right here. We'll have to go on a slant, sorry. Minus, and then it would be, bottom times the derivative of the top minus top times the derivative of the bottom. The derivative of the bottom is just cosine x, all over the bottom squared. All right, let's multiply that out. We'll multiply the negative sine x through, and we'll multiply these two together, and we're going to end up with the derivative is, we've still got that 1 plus sine x squared in the bottom, but now we're going to have negative sine x minus sine squared x minus cosine squared x. All right, I'm going to come over here with this. I'm going to factor out a negative 1. All of the terms have a negative in it as a coefficient. And that is going to make something really special happen here as we do that. So let me factor that out. So we're going to end up with negative times sine x plus sine squared x plus cosine squared x all over 1 plus sine x quantity squared. And then hopefully you remember this part of it is a Pythagorean identity, so sine squared plus cosine squared equals 1. So we end up with negative quantity sine x plus 1 over 1 plus sine x quantity squared. That is a beautiful thing right there, because our sine plus 1 and our 1 plus, or one of our 1 plus signs down here cancel. And so we end up with negative 1 over 1 plus sine x as our first derivative. Our second derivative, well, that makes life a lot easier here. Just for the purposes of taking the second derivative, I'm going to write this as f prime of x equals negative 1 plus sine x to the negative first power. All right, so when we go to take the derivative, I'm going to use the chain rule instead of kind of a degenerate quotient rule right here. So when I go to take f double prime of x, I'm going to bring this negative 1 down to the front, so it's going to turn it positive, and then I'll keep the inside the same, 1 plus sine x. I'll decrease that power by 1, so it becomes negative 2, and then I have to take the derivative of the inside. And so that is going to be cosine of x. And then I'm just going to rewrite this so that it is cosine x in the numerator and 1 plus sine x quantity squared in the denominator. All right, we're ready to go on to the next page, and I am going to, while we're at it here, transfer these onto this page. So we're going to write the original function f of x is cosine x over 1 plus sine x. F prime of x is negative 1 over 1 plus sine x. And f double prime of x, whoop, you might not be able to see that anymore. F double prime of x is equal to cosine x over 1 plus sine x quantity squared. All right, just so we don't have to keep flipping back and forth. Okay, the x-intercepts. So x-intercepts come from the original function, and so we're looking for where is the function equal to 0. All right, so, well, that's going to happen just when the numerator equals 0. So when is cosine equal to 0? Well, that happens at pi over 2 and 3 pi over 2, but remember that we've restricted our domain to, so actually let's write that in here. Domain is open interval negative pi over 2 to positive 3 pi over 2. So cosine is 0 when x is positive pi over 2 and positive 3 pi over 2, but notice 3 pi over 2 is not in our interval, so it's only going to be x equals pi over 2. All right. For the y-intercept, again, we go back to the original function, and it is where, when we put 0 in for x, that's when we're going to get our y-intercept. So if I put 0 in for cosine, I get 1. If I put 0 in for sine, I get 0. So I've got 1 over 1 plus 0 is just 1. So our y-intercept is 0, 1. All right, vertical asymptotes, again, they're not in our interval, but we're going to put them there as just kind of as borders here. So at x equals negative pi over 2 and x is equal to 3 pi over 2, just to kind of frame our interval. We'll end it with 2 asymptotes there. Right, horizontal asymptotes, there are no horizontal asymptotes in here. And again, let me just write our original function, cosine x over 1 plus sine x. As we let x approach infinity, because again, that's what's happening with horizontal asymptotes, we're letting x go to infinity, and we're seeing if the function kind of calms down at any point. As we approach infinity, really that 1 is insignificant to us. All right, it's not going to do a whole lot for us. It will determine where where vertical asymptotes are. It would change where vertical asymptotes are, but for the most part, this function is going to behave very much like cosine x over sine x, which is just cotangent. And if you remember, cotangent looks like this. It's got asymptotes, it has a period of pi, and so it's just going to do something like this. All right, it's a decreasing function. And so it's never going to end up calming down and approaching a horizontal line. And so we're going to say that there are no horizontal asymptotes. Okay, critical numbers come from our first derivative. All right, so we're trying to see where our first derivative is either 0 or it's undefined. All right, the 0 comes from the numerator, right? There's no way that -1 is going to equal 0, so there are no critical numbers coming from the numerator. And it could also come from the denominator. Where is the denominator undefined? Well, that's at -π/2 and 3π/2, but they're not in our intervals. And also they were not in our domain to begin with. So we're going to say that there are no critical numbers. All right, possible points of inflection come from our second derivative. And again, it comes from where is the numerator 0 and where is the denominator 0 that's still part of the original domain. So our when is cosine 0, we also we answer that question for the x-intercepts. The only place on our particular interval is going to be at x equals π/2. Again, it could also come from where the denominator equals 0, but we've already said that the denominator is 0 at points that were never in our domain to begin with, so we can't include them. Okay, for symmetry, we're looking to see, is f of -x equal to either f of x, or is it, is f of x equal to the original function, or is f of x equal to the complete opposite or the complete negative of the original function? So let's plug those in. So we get cosine of -x over 1 plus sine of -x. All right, since cosine has y-axis symmetry, again, we know that because, well, it looks like this on the right side of the y-axis, it looks like this on the opposite side of the y-axis, and we have that mirror line right there. So cosine of -x is cosine of x. It's the same on both sides. Sine is not even. It has origin symmetry. Again, let's just sketch that so you can remember that. All right, here's what it looks like on the right side of the y-axis. On the left side of the y-axis, it looks like this. All right, and so notice it has origin symmetry. If I put this value in for x, I get positive, whatever it is, and then I come down here and I get the negative version of it. All right, so then sine of -x is the same thing as negative sine of x. So we've got 1 now minus sine of x. That is neither exactly the same as the original, and it's not the exact opposite of it. So in terms of symmetry, there is none. Okay, so for our test intervals, those are going to come from if our endpoints, if there is an endpoint to our interval. Again, all the ones that we've done so far have been -infinity to +infinity with certain exceptions for our vertical asymptotes. Here we're actually going to start at -π/2. And then we break an interval, or our endpoints of intervals come from critical numbers and, critical numbers, possible points of inflection, and vertical asymptotes. So this is a vertical asymptote right here. There are no critical numbers. The next opportunity here is at π/2. So we're going to go -π/2 to π/2. And then our next one is going to be π/2 to 3π/2. Again, this is the end of our interval because it's where a vertical asymptote occurs. All right, so those are going to be our intervals. Okay, so let's put them in here. So our first one is -π/2 to π/2. And then x equals π/2 is going to be our next point. And then we have got, why do I have so many lines right here? Actually, let's put in, I know why, because I put in -π/2 just so we could note that that is a vertical asymptote right there. So sorry. Hope you're not doing this in pen. So let's say x equals -π/2. Again, it's going to be undefined everywhere, but we're just putting that there so we can comment that there's a vertical asymptote here. And then -π/2 to π/2. And then x equals π/2. Again, that's our possible point of inflection. And then we've got π/2 to 3π/2. And again, we're going to put x equals 3π/2 just so we can note that it is a vertical asymptote. Okay, We're going to X out in here. We're going to X out in here because we cannot find the value of the function on an interval only at these points right here. We will pick test points in here. So between negative pi over 2 and positive pi over 2, I'm going to choose 0 as my test point. And from pi over 2 to 3 pi over 2, I'm going to pick pi as my test point. And here I'm going to comment that the reason that this pi over 2 ended up in the table is because it's a possible point of inflection. And again, this is the open interval endpoint of our interval. This is going to be a vertical asymptote and a vertical asymptote. And we'll comment about that in just a second. So again, if we put negative pi over 2 into our original function, again, we've got this little box over here, just so that we remember what everything is. So when I put negative pi over 2 in here, I get 0 in the bottom. This is undefined. All right, I put pi over 2 into this. Cosine of pi over 2 is 0. And then sine of pi over 2 is 1. So we get 0 over 2. So this is 0. And then 3 pi over 2, again, that is the endpoint of the open endpoint of our domain. And so this is undefined here. In fact, let's just comment because it's got a 1 plus sine x in the denominator of each of all of these. It's undefined, undefined, and then this is undefined and undefined. So this is a vertical asymptote, and this is a vertical asymptote. Okay. So now we've got the 3 legitimate things that we need to test here. All right, so now we're going to do the first derivative, and our first derivative is negative 1 over 1 plus sine x. Again, numerator's always going to be negative, so really we're just curious to see what's going on down here with the 1 plus sine x to see if it will reverse course or not. All right, so when I put 0 in for sine, I end up with 0 plus 1 is 1, so negative 1 over 1 is negative. I put in pi over 2 in here, so negative 1 plus sine of pi over 2. Sine of pi over 2 is 1, so 1 plus 1 is 2. Negative 1 over 2 is negative. All right, again, we're remembering that this was a possible point of inflection, so we shouldn't be concerned that that's not 0 here. We can't get any zeros for there. All right, and then I put pi in. So cosine of, negative 1 over 1 plus sine of pi. Again, sine is 0 at pi, so we've got 1 plus 0. Negative 1 over 1 is negative 1. And then let's do f double prime. All right, the second derivative, we're going to put our values in here. So here we've got cosine of 0, which is 1, over 1 plus sine of 0 is, again, sine of 0 is 0, so 1 plus that is 1, so 1 over 1, this is positive. We put pi over 2 in, cosine of pi over 2 is 0, and then 1 plus sine of pi over 2 is 1, so we're going to get 1 plus 1, so we've got 0 over 1, so this is 0. And then we do the same thing for pi. So cosine of pi is negative 1. And then sine of pi is 0. So we've got 1. Actually, this is always going to be positive unless it's 0. So it's not 0 here. So we end up with negative 1 over something positive. So this is negative. Okay, so then let's make our conclusion. So this is decreasing, concave up. This is decreasing, and it's a point of inflection. Again, we know it's a point of inflection because we thought it might be a point of inflection, and we see that it changes from concave up to concave down here. And that's exactly what a point of inflection does. And then this is negative here, so it's decreasing, and then it's concave down. Okay, we're ready to graph. Okay, so we've got not a lot to work with here. So we do know that, well, let's see. Let's just put our x-axis right across the middle there, and our y-axis right down the middle here. Okay, and so we know we need to get to 3 pi over 2 as our highest value. We need to get to negative pi over 2. I'm going to skip count here, so that's 1 pi over 2, 2 pi over 2, or just pi, 3 pi over 2 right here. This would be 2 pi right here. And then we'll do the same in the reverse direction. So negative pi over 2 is going to be negative 2 pi over 2, which is just negative pi, negative 3 pi over 2, and then negative 2 pi. Again, we only need this strip right here, but we'll just kind of continue it on. So negative pi over 2 is going to be a vertical asymptote, and negative 3 pi, or I'm sorry, positive 3 pi over 2 is going to be an asymptote. Okay, let's add some stuff here. We know that our x-intercept is going to be at pi over 2, so let's put that dot right there. We also know, shoot, I didn't label the y-axis. Let's do 1, 2, 3, 4, 5, 6. So I'll just number the even ones. So 2, 4, and 6, and then we'll do the same down here. Negative 2, negative 4, and we don't have room for negative 6. Okay, so we know that our y-intercept is going to be at 0, 1, which is right here. And we also have, let's see, I guess that's it. I was going to say I have plotted a point here at pi just to give us a third point. If we plug pi in to our original, cosine of pi is negative 1. And then 1 plus sine of pi is 0. So it's negative 1 over 1. So at pi, it's that. All right. It looks like, again, as we recall, that it should look very much like cotangent of x. I see that in here. I see these vertical asymptotes. But let's use our table. So from negative pi over 2 to pi over 2, it's decreasing but concave up. So again, that's going to look something like this. All right, decreasing but concave up. At pi over 2, it's a point of inflection. All right, and so it's going to switch to decreasing. Well, it is decreasing still, but it's going to switch concavity. And so now as we get into this region right here, we know it's going to switch to still decreasing, but now concave down. And so we're just going to turn it so now that it's concave down instead of concave up. All right, so again, very cotangent-y. If we were to do the same thing in this, we know that it's going to come down. We're not going to see where it's going to hit, but actually it's probably going to hit right here, just based on the mirroring that we could do. So it would look like that. And then we would have something very similar over here. So right here we would have, you know, pi over 2 units away from our vertical asymptote, we would have a point at 1, negative 1. Again, this is not 1, negative 1, but now it's in the same relative position as this. And then we would have a point here, and we would have a point here, and our next vertical asymptote would be right here. So again, if we were to put in another cycle of this, which you're not asked to, but I'm going to because we have the space, it would look like this. So again, still decreasing, concave up, and here at that other point of inflection, it would switch. We were only asked to graph this, so this is just a bonus right here to have it, but it would continue in that pattern. Okay, hope that helps. All right, bye.